So in this video I'm going to talk about intermodulation distortion. I'm actually going to break it into two videos to explain the two kind of fundamental types of intermodulation distortion. The first, and certainly the more mathematically simple, is amplitude modulation, and then in another video I'll talk about frequency modulation. But the thing that kind of links these two types and makes them different from other forms of distortion, usually we think of distortion as this kind of wave steepening effect which adds frequency components, harmonics, which are integer multiples of some fundamental. And intermodulation distortion is very different in that it adds extra frequency components that are multiples of the sum and the difference of two frequencies. And so two frequencies need to be present for intermodulation distortion to occur, and it's the sum of those frequencies and the difference of those two frequencies and multiples thereof that are the extra components that are generated by this type of distortion. So markedly different from, I don't want to say traditional distortion, but the type of distortion that we're probably more used to thinking about. So we start right off with this trig identity, which is basically sine of A times sine of B equals cosine of A minus B minus cosine of A plus B. So here's our difference and here's our sum. It's worth noting also right off the bat that neither of these two frequencies show up in the output. So we started with some omega 1 and omega 2, but this isn't really a guide to what's going to happen in the frequency domain because these two terms are multiplying one another. And so in order to know what frequencies are actually going to show up in the frequency domain, we have to have that isolated trig function, that isolated cosine of term. When you have these two trig functions multiplying one another, this is actually the result. And so why also this is amplitude modulation? I think you can think about the fact that we would often have a single trig term here, sine of omega 2, let's say, and there'd be some scalar coefficient out front, a sub 2 times sine omega 2. And sine, a trig function, would be centered around 0 and bound between negative a to positive a. Well, there isn't a scalar out front, there's another vector out front, so instead of being multiplied by this scalar amplitude, it's being multiplied by this constantly changing amplitude in the form of this other sine function, and that's why this is essentially amplitude modulation. So to expand this out a little bit, I'll add those amplitude coefficients, and that's because we do commonly think about the individual trig functions as having some arbitrary amplitude, a sub 1 and a sub 2, but since everything's just multiplied together, we can collect these terms and then stick it back out here in front of the term that we know is the result of this sine times sine multiplication. And what's really going to get interesting actually here is when we add a DC offset to these two sinusoids. So it seems pretty trivial. You have a sine times a sine. They're both centered about 0. But actually, things really start to happen when one of those is no longer centered about 0, or when both are no longer centered about 0. So thinking about it as simply a DC offset makes it seem kind of trivial, but you can see here that now all of a sudden I have to do some factoring, and I'm going to get 3 extra terms. So I'm still going to have this sine times sine, which is going to blow up into that difference and sum term due to the trig identity, but I'm also going to have a k1 times the sine omega 2 term, and I'm going to have a k2 times the sine omega 1 term, and I'm also going to have a k1 times k2. So factored out, that all looks like this, and so this is a lot. And where before we didn't have the original two frequencies present, the existence of some offset is what makes the original two frequencies show up in the output, which, again, if you think about it that way, is a little strange, but the algebra bears that out. It's also interesting that it's an offset in the opposite waveform that creates the presence of that waveform. So in order for omega 2 to show up in the output, omega 1 has to have some offset. You can see k1 is the coefficient to sine omega 2, and vice versa. And then lastly, this term is the offset of the output. So all these, these are basically two individual trig terms, they have some arbitrary magnitude, but they're centered about 0. This is centered about 0. This is centered about 0. This is the only scalar offset term. So again, if only one of the original two waveforms has a DC offset, the output will not have a DC offset. Only if both have a DC offset will the output have a resultant offset. Because if one of these two terms is 0, then obviously the offset is 0. So to essentially prove this, we're going to use both methods. This is kind of the simpler method, just multiplying the two waveforms together. And then this is the method where everything is factored out. Of course, looking at it this way, is useful because it shows us where all the individual frequency components come from. It's not necessarily intuitive looking at it this way. In fact, we'd kind of, at least maybe just by first observation, say, yeah, this means that some frequency at omega 1 and omega 2 are going to show up. Those two frequencies are going to show up. And in fact, they don't show up in many cases. So this makes it more intuitive. So we'll prove, of course, that these two things are equivalent. And we'll start by having the DC offset for both be 0. And of course, what that's going to mean is that the two original frequencies, 201 and 857 hertz, are not going to show up. It's only their differences and their sum that are going to show up. And that's, again, because these k terms are both 0, which means all three of these trailing terms here are going to go to 0. And we're only going to be left with this. And the difference frequency comes out to 656, negative 656, and the sum term comes out to 1058. The negative here doesn't matter. For reference, cosine of negative n just equals cosine of n. So the fact that this is getting passed into a cosine function means it really doesn't matter. If it was getting passed into a sine function, it would mean 180-degree phase shift. That's it. There's nothing wacky. It's a little jarring to see a negative frequency, but sine of negative n equals negative sine of n. So that means there'd be a 180 degrees phase shift. But that's it. So there are two lines here for each. They're right on top of each other, so it's essentially impossible to tell that there are two lines. But the two frequency components show up where we expect, at 656 at 1058 hertz. Now, we only have those two components, but if we add, or if we create some offset now, k1 and k2 are non-zero, then we know now all of a sudden that we're going to get two more components at these original two frequencies. And because these are the coefficients of omega 1 and omega 2, we can also verify that the amplitude we see in the frequency domain is correct. So A1 times K2, A1 is 1, K2 is 1, so that's just 1. And then K1 times A2 is 0.2 times 0.5, which means 20 dB. So the coefficient to the omega 1 term is 1, and the coefficient to the omega 2 term is 20 dB down from this term. This one is just 1. This one is negative 20. This is actually negative 20. So we have the two additional frequencies, which is what we expect. They're at 201 and 857. And if we zoom in, we can see this one's about 88 dB, this one's about 68, so that's 20 dB between them. And we expected that it would be the omega 1 term that would be higher. The omega 1 term has a coefficient of 1, and the omega 2 term had the coefficient of negative 20 dB. So there we go. And then lastly, we can see the way that this final term, this is just the scalar term, affects the output. K1 times K2 is 0.2, and we can see that the offset of the resulting waveform is 0.2. The yellow line here is a moving mean, so it's not a mean of the entire waveform. It's kind of like a window, a sliding window mean, and so you can see the little perturbations that kind of follow the shape of the waveform, but it's pretty well converged on 0.2. So the offset, as dictated by this term, is K1 times K2, in this case 0.2, as we expect. And then lastly, I'll just show using 201 as F1 and 857 as F2, the sum and difference terms were both much higher in frequency than the lower of these two terms, But when these two terms are closer together, you can pretty much see this by observation, but when these two terms are closer together, just to show it explicitly, you can actually get a resulting frequency that's much lower than both of them. So the difference term here is obviously going to be 857 minus 801, which is 56 hertz, significantly lower than them both. And the idea of whether or not undertones could be created by natural phenomenon is the question that kind of started this topic for me. And we can see that the 56 hertz tone, it results when these two are 56 hertz apart from one another. And having a frequency that's much lower than the two input frequencies can be dangerous for some systems. And so you have to be careful if you have some system that does create intermodulation distortion, that you could get this resulting really low frequency at the output. So that's it for this topic. I'll move on to frequency modulation in the next video.